we tend to think of things as humans. We tend to think of things as being the sort of the fault of the person, right? And so it's like, oh well, oh that person's fat because they're a glutton or because they're lazy.
Hmm.
Whereas I believe that it is it's all the system is more driven by the internal choices that the cells are making and the sort of state of the cells, and that is causing us perhaps to overeat because our our hunger circuits are dysregulated, or simply that in a different state, even if we did overeat, that fuel would just burn away. And it's not really about caloric consumption at all.
Our neighbor's choice.
Well, we're glad to have our returning friend to the show. We haven't seen him for some time, but he has been back and he's back in black. He's got a new series at fireinaBottle.net where he's really hitting the ground running with some nice metaphors and analogies, sweeping us through intelligently designed posts about the Cambrian explosion. Brad Marshall joins us. How you doing, Brad?
I'm doing great, David. Thanks for having me.
It's great to
It's
see you.
exciting
Yeah.
to be. It's exciting to be getting back out there. I was kind of. I was quiet for a while. I was hiding.
No, I like the way you do it because you do have kind of a seasonality to your online presence, which is really cool. Is that intentional, or is it just that it comes with the temperament that you have in a certain season of the year?
Yeah, it's more the second one. It's more the second one. I don't, you know, I don't love social media at all. It's
Yeah.
sort of a. It feels like a chore for me to do it, and so
Yeah.
I have to be in a zone where I'm focused and I can really think and focus on that. I moved to Buffalo to I'm in this. I am running a lab in Buffalo, and I moved for that reason, and so that has taken up a lot of my time. But now I've settled back in, and I can start to spread my focus a little bit again. So
Yeah.
it's very exciting, and I've had a lot of time to think in that time off. So now when I come back, the ideas are new and fresh, and we're not just recycling the same content, which is cool.
Yeah. Now you've got some new insights and some great metaphors. It's so hard for folks to catch up to your level of, for those who are not familiar, you have a background in molecular biology, right? You went to Cornell. You've done a lot of work in genetic research. You're also a former pig farmer, right? You're retired in
That's
that
correct.
field. Are you a cheesemaker?
I have made cheese.
Okay.
I wouldn't call myself a cheesemaker. I did go to the. I ran a restaurant, and I did go to the French Culinary Institute. So,
Yeah.
um,
Is that
yeah.
your biggest passion of all, or is it the things that you're doing now? I mean, in terms of your research.
No, I mean I love that. The biggest passion is what I'm doing now, and the research and the writing, and yeah, and just the lab work as well. But we can't.
Yeah,
I can't say too much. I can't say too much about that today, but
yeah,
we'll get there soon.
yeah. I mean, you've got this series that I kind of wanted to give people just a general entrance into kind of why they should take a look at it. I've enjoyed reading the posts,
Yeah,
although
and I just want to say, if people go to fireinaBottle.net, there's a little link at the top that says blog index, and you can and all of the news stories are called the whistle pig and the hare, which is the name
yeah,
of the article. And let me just set it up. That's the name of the series. That is because the whistle pig is a country name for a groundhog,
yeah,
and a hare is of course a rabbit. And
but
one of the
totally
things
different.
right, you see, but they're both rodents. They're both hind gut fermenters, which means that they can take in a lot of fibrous mass and ferment it in their gut. They both eat mostly grass, and they both live in the exact same niche, and yet the groundhogs are very fat and the rabbits are very lean. And so that's how we open the series, is saying why and how can this be. Clearly, everything is in the grass that a hindgut fermenting rodent needs to become fat,
Right.
but the rabbit chooses not to.
Right. And so then you go on to fattening is about oxygen, right?
Yeah,
So talk a little bit
right.
about that. We're just going to go through a little overview of these things, and you go as deep into these little points as you'd like to. I don't want to spoil everything, but I do want to give people some appetizers so they'll take a look, right?
Right, sure. So the analogy that I make is to a wood stove, right? I grew up in the country, or people had wood stoves, and you've got a wood stove. You load at the end of the night, you put a couple big fat logs in there, and then you shut the damper 98% of the way shut, so that just a trickle of air can get in there, right? So you limit the flow of the oxygen, and the logs burn very slowly like that, so that in the morning you open the door and there's still some wood and some coals left, and you can get the you can get the fire going the next morning without a problem, and the house stays reasonably warm overnight because
Yeah.
there's still a little bit of fire going. But the point is that what determines how much wood is left over is how much oxygen you allow into the fire to let it burn, right? So if we think about a mitochondria as a little furnace, the limiting factor in burning the fuel, the carbohydrates, the fats, is the amount of oxygen that is allowed in, right? And so that kind of sets up the story from a mechanistic perspective, and we haven't really gotten yet in the series to how that happens. But I use a simple story from a scientific paper. They were looking at these things called copepods, and copepods are they kind of look like little shrimp, but they're a lot smaller than shrimp, and they are kind of the base of the marine ecosystem. So algae is the primary producer. The copepods eat the algae, and the tiny fish eat the copepods and become big fish. And so copepods sit at this really interesting junction because um, they're consuming a lot of polyunsaturated fat, but they're also at the junction between herbivory, things that eat plants, and carnivory, the things that eat the copepods. And so it's a very interesting model to me. And one of the things that the copepods do when they want to fatten up, when it's time for them to reproduce, they need to fatten up. And so what they do, they're not strong enough swimmers to beat the current. They just sort of float along with the current, but they can swim up and down.
Yeah.
And so what they do is they swim deep down to where there's low oxygen. They call it the oxygen minimum zone. And by going down to where there's no oxygen, that allows them to build up their fat reserves, because they're essentially closing that damper, right? And they're not allowing the fuel to burn. Instead, they're encouraging the fuel to build up.
Yeah.
And so that is the analogy in the beginning.
Yeah. And so you kind of go on this concept of oxygen and lack of oxygen. You have this post: pregnancy is hypoxic. So that is something that is part of the one of the puzzle pieces here that you're starting off with.
Yeah. So when we think about, right, I'm an evolutionary biologist, David, obviously, as you know, and I did say in a post, one of the posts, I said, if all of this stuff seems pretty magical, and if you want to take that as existence of a higher power, that's fine by me, right? But I was thinking about you when I wrote that line, David, to be honest with you. but I look at it obviously from the lens of evolutionary biology, and so there was a point where there was no oxygen in the Earth's atmosphere, and everything was just bacteria then, and everything just was growing and multiplying and growing and multiplying. And then as oxygen came in, the cells get more complicated. That's when you start having mitochondria and nucleus and all these other things that the bacteria don't have. And those things are just single-celled organisms, right? But then at some point, you start having these multi-celled organisms.
Yeah.
And the stem cells behave a lot like the bacteria that were alive when there was no oxygen in the air, right?
Yeah.
The stem cells are typically starved of oxygen, and that puts them, like the copepod that swam to the oxygen minimum zone to grow. That lack of oxygen, when you take the fuel in, you can't burn it, and so it tends to accumulate, right? You can use it to make fat, you can use it to make protein, you can use it to make membranes, but you can't burn it. And so that lack of oxygen looks growthy, right? And the of course, early in pregnancy, the yeah, the I'm not getting the word. The baby is growing very quickly, right? And so those cells are essentially growing flat out, right? They're full on. They're doubling every 24 to 36 hours, something like that, as the embryo is growing. And so what happens is the mother blocks flow of oxygen to the uterus to make the uterus hypoxic, which is to say low in oxygen, much like the earlier Earth, which is where those stemmy kind of cells evolved, those cells that would just constantly grow and reproduce and divide. And the mother wants the cells to do that. And so the mother restricts oxygen flow to the fetus, and that's what allows that early explosive growth. And then what happens is, as the baby gets closer and closer to term, blood flow is restored, and the amount of oxygen in the uterus steadily increases, in that the oxygen itself encourages those cells to differentiate, and instead of being growthy and replicating, they become specialized, and that's what we call differentiated cells. And that's when they start using their mitochondria, and they start doing oxidative phosphorylation, which just means using their mitochondria to generate ATP, which is cellular energy. And they become specialized, they become liver cells, or they become neurons, but once they become a liver cell or a neuron, you don't want them to divide anymore, right? You want them to sit in place and do their job at that point. And so that process is actually stimulated in part or in large part by the introduction of oxygen. And once the mitochondria start to work, they start to create reactive oxygen species. And those are actually crucial signaling molecules that tell the cell, okay, we're an adult, grown-up, differentiated cell now, right? And those kinds of cells are fundamentally different than the types of cells that existed before there was oxygen in the atmosphere.
Yeah.
And so the mother is essentially recreating the conditions of a billion years ago in the uterus.
Dr. Lewis Coleman, who is a anesthesiologist that I was introduced to by a friend of mine named Steve Scott, who has carbon genetics. Have you heard of that?
No.
The CO2 bodysuit, which I have to say I enjoy.
Okay.
I've been using it. It's very relaxing. 100% CO2, no forcefulness into it. There's no aggressive way in which you receive it, of course. It's just a very relaxing suit. No surprises. And, it's a wonderful experience to be in there. And that's it's not 100% CO2, but I'm sure that's kind of like that environment, the early Earth. I mean, that's what Dr. Lewis Coleman said. He said the early Earth was like hell. It was hot and heavy in the CO2, and that's what made everything go so crazy. He thinks the key is those vents in the ocean. That's where all that rich
thermal vents
and all those animals were just blowing up. The archaea. Is that kind of in line with what you're saying here?
That is certainly in line with my thinking, and I think that is what many people think, is that life started in those thermal vents. And exactly as you said, the early Earth atmosphere was what they call a reducing environment, which means, well, it's the opposite of what it is now, which is an oxidizing environment, right? And it was the algae that flipped the script on that, right? Because what the algae do is they take the carbon, right? So the atmosphere was all carbon dioxide. It was hot. The algae take in that CO2, and they bubble off the oxygen, right? The hydrogens get used in building fats or whatever they need to build, right? the carbons, I mean, get used to build fats. They get used to build carbohydrates, right? The plants take those carbons from the CO2 to build sugar, essentially, and fat, and then they bubble off the oxygen. And so that's what happened over time. The plants converted all that CO2 into oxygen and water ultimately. And the carbon, of course, is like got turned into coal or animals or biomass or whatever.
And that's what he said. That's why there's such little CO2 in the atmosphere. It's because life ate it all up, you know?
Yeah, no, that's exactly right. And then what happened was, the plants actually brought the levels of CO2 so far down that we had for like a billion years, we had something called snowball Earth, where everything was frozen solid all the way around.
Yeah.
And life continued going in the oceans, and then eventually, you know, for processes that I don't entirely understand, we got back to where we had a climate that we could, you know, get around in, and everything wasn't frozen anymore, which is nice.
Yeah.
I prefer that.
Yeah. I do too. I'd rather it be a little warm instead of a little frozen.
Yeah.
With the CO2, you know, that's something that I missed it when I used to, you know, and you were one of the special people who got to interview Ray Pete with me on our show years ago. But that's one of the things that I didn't catch about his work when he was alive was the CO2. So afterwards, I got interested in it, you know, and
Right.
And I went to I did some research and stayed up at altitude close to about 9,000 feet for not enough time. I had other things that pressed me to get back to the other things. I wanted to stay longer, but that I thought that was an interesting kind of introduction to this idea about messing with the oxygen has some kind of effect on your metabolism, you know. And I didn't stay there long to get a real significant, you know, experience with it.
Where was that?
In Colorado.
Okay.
Yeah.
Higher than Boulder.
Yeah, I went to a little gold mine town called Victor, Colorado.
Okay.
That's about 9,000 feet.
I think Mexico City is like 7,000 feet.
Yeah. And so I went there, and I remember there was a study about they put rodents, they put them at the high elevation, close to about 9,000, 10,000 feet, and they noticed at first that they were just still for a little while, for a few, like a day or so, and then all of a sudden they just came alive. You know, metabolism was just raring to go. So there was like a little processing where they had to kind of like adjust, right?
Right.
To the lower oxygen in the atmosphere, and then the metabolism boosted them up and they were ready to go. And I kind of noticed that too. Like when I first got to that level, I'd been going up, I'd been staying at other places. Altitudes was just going up as I went. And I just noticed at first, see, like, God, I feel like so down, you know, and what kept me positive was like, oh, I'm probably going through something like those little rodents at first. It was like 2 or 3 days. I was just like very like despondent, mentally feeling like despair. Like, why the hell am I here? All of a sudden, like everything was fine, you know, and I had my energy back, and it's like, so there was like a little bit of a loading time or something, you know?
So in the articles, I'm planning on writing 2 articles for the blog this weekend. And in one of those posts, one of the little stories or pieces of evidence that I use is, so they put people on a plane, flew them to Denver or Boulder, I don't know, somewhere in Colorado, and they measured the amount of oxidized lipids in the bloodstream. And within hours, you see like a doubling in the amount of these, oxidized PUFA, right? The oxylipins, or the linoleic acid oxlams, oxidized linoleic acid metabolites, they call them as well. So within hours of going up in elevation, you see this rise in polyunsaturated fats. And that's actually one of the key pieces of evidence that I'm using to put this theory together that is going to be published this weekend, probably by early next week. So that's exciting. I don't know when this comes out live. Perhaps those articles will already be live by then. But
yeah, I think I think I what I enjoy is this, and I've told you this before, is where truth can be ascertained at different, different journeys and different pathways, finding common, evidence that helps support this ultimate truth that kind of gives us insight into what's going on, you know. Um,
Yeah.
and Denver's at 5,000 feet, and Dr. Pete said seemed like the real strong health effects happen at 8,000 or higher, and I don't know why that is, but
Hmm.
7,000 or 8,000, I don't know, but
Yeah.
I'm not sure what exactly, what the percentage of what in the blood is. Maybe they could measure that.
Right. Yeah. Yeah. Well,
Man, you
my
give me
suspicion.
something to measure some of this stuff next time I go up there. I'll be going there probably in the summer.
Yeah. All you need
And,
is a high pressure liquid chromatograph. They're only like, you can get into one of those for probably a quarter million, no problem.
okay.
They're a little big to take on the plane, though.
Yeah. Okay. But
You'd also need a mass spectrometer. I
yeah,
should say you need
right.
HPLC MS to measure that. Yeah.
So is it that the low oxygen with increase, that's something else that I was studying. And again, I'm just kind of throwing just different little
Well,
points that
let,
interested
let,
me
let, let me
about
be let me
oxygen.
be clear though that that's a temporary status, like
Right.
you say. So that happens within hours. But then if you look 2 days later, what actually happens is the blood vessels open up,
Yeah.
dilate, I guess is that word. And so,
Vasodilation. Is that
so,
what it?
so ultimately, you wind up with more blood flow to those organs when you go to that higher elevation. But like you say, it takes a couple of days.
Yeah. Yeah. That's what they noticed with the Maasai, right? That their blood vessels were really enlarged, right? They had strong, and they're higher
Yeah,
elevation. So I don't know if that has any. I guess
right. That's interesting.
that seems to be the key, right? Is to be high elevation. You have the lowest rates of obesity, lowest rates of cancer mortality, all of those things. So there's some kind of the stress of having less oxygen up there puts your body into a high metabolic rate, right? It seems to be the
Well, I
general.
think it's more, like you say, I think it's more keyed into the CO2 actually, right? So the magic here, for people who don't know, is that your most right. So your body controls the oxygen flow through the organism pretty tightly, right? And so one of the tricks that it uses is cells that are metabolically active release more CO2, and so the CO2 actually competes for the oxygen at the site of the hemoglobin binding, and so the hemoglobin releases more oxygen in areas where CO2 is higher,
Yeah.
and so that flow of relatively high amount of CO2 coming out of high metabolically active tissues allows the body to divert oxygen there.
But there's
And
not higher
so,
CO2 in the atmosphere at the top, right? It's just that there's lower oxygen, which your body produces more CO2 as a response, right? Is that correct?
well, yeah,
The
I don't
CO2
know.
tends to stay lower, right? That's kind of
CO2 is
strange.
lower. Yeah, the CO2 is all being produced by your body, right? The
Yeah,
levels of CO2 in your body are much higher than what is in the atmosphere, but the
right. Right.
the oxygen, your body compensates for the lack of oxygen by opening up the blood vessels to allow more oxygen flow in. But I think it's something, and I'm not an expert in this field. I've thought
Yeah,
about it a little bit, not a lot. I think it has something to do with changing the elevation, changes the relative pressure at which the CO2 comes out.
yeah,
But I'm not gonna
yeah.
argue that I definitely have that mechanism right because I'm not really sure.
Right.
Um,
So it's that your body it produces more CO2, and it allows it, from what I understand, it allows that increase in CO2 allows your body to utilize oxygen in a more favorable way, in a more effective way.
right,
Actually
right.
mitigate some of the toxic effects of oxygen, right? Some of the damaging effects of oxygen.
Yeah, I mean, I don't. I think oxygen is. I'm a big fan of oxygen.
Yeah.
I think to some extent the toxic effects of oxygen are a little bit overemphasized. I think that we've dealt with that situation pretty well. Oxygen is good.
But not like in health situations, they always give people 100% oxygen, and that makes them hyperventilate. That makes them have a harder time healing, and that's what
Yeah, well,
Dr. Lewis Coleman
sure.
showed as an anesthesiologist when he would increase the CO2 and actually use some of the techniques that they used to pioneer in the 1950s, the nurses, when they would have anesthesia, that was more effective when they would get more CO2 in there for healing, for recovery, for everything for the patient,
Well, yes, but you also, I mean, also the example of 100% oxygen is obviously, that's five
Yeah.
times the level in the
Yeah.
air. So that's
Why do they do that though for patients?
within sort of normal ranges of oxygen. I
Yeah.
like oxygen, but
Yeah.
but I agree with you. There's something interesting that happens in high elevations when the oxygen level drops a little bit as
Yeah.
well. But I'm not a huge believer that oxygen is toxic. I think
Yeah.
it's just all part of the balancing act of
Of the fuel, right? Getting the fuel mixture right.
yeah, yeah, exactly.
And then you have the issue of that Ray used to mention a lot, the naked mole rat. Have you heard of
Yeah.
that? Yeah. Who bear
Remind me. I think I
he
read it
he,
once, but
he is the little rodent that's very similar to a regular rat, but they have a lower metabolic rate. They tend to bury themselves in the ground and limit oxygen, just like that little placenta you were talking about, that little
right.
fetus. And
Yeah,
that makes them almost impervious to diseases like that we would typically associate. They live much longer
right. They're
than the
letting
typical rodent their
the
size.
CO2 built up,
So what does
but
that
they
mean?
also
What does that mean for us? Does that mean that you know Coleman was saying if people could sleep in a CO2 rich environment every day, it would really help with anti-aging effects and anti-obesity, all the big things that everybody's trying to figure out. Is that really
yeah. I mean, but I will be honest with you though. This is verging a little bit outside of my what I know a lot about. So I
yeah,
don't know how much I have to
yeah,
add to the CO2 conversation.
yeah, yeah,
I haven't gone fully down that rabbit hole yet. I think it's interesting, but I
yeah,
don't. Yeah, I don't. I'm not sure.
yeah. Well, those are just the things that come to mind when I'm hearing some of these posts that you're making, where you're talking about the environment of early Earth, the environment of the fetus and the placenta. I only hear a clue about the carbon dioxide factor, but
Right.
you're
Sure.
looking at other things there, right?
Yeah, I'm thinking more about the oxygen flow,
Yeah,
which is the opposite side of the equation. I mean, they are the CO2 and oxygen are linked.
yeah,
They're interchangeable, and yeah, you can't get one without the other, sort of, right? The CO2, I would say, is the CO2 is the reduced form of oxygen. Oxygen is happier in the CO2. When it's O2, it's relatively unhappy, which is why it tends to set things on fire, because it wants its electrons back. But the carbon molecule is a relatively unwanting of electrons compared to oxygen. So in CO2, oxygen is very happy because it is essentially stealing some electrons from those carbon atoms. And that's why the in the reducing Earth, everything was CO2, and the oxidizing Earth, a lot more is oxygen. So one of the things that I'm very interested in is the relationship, right? I talk a lot about how cells can either be anabolic or catabolic, right? And so in a catabolic state, the cells of your body are primed to burn fuel oxidatively, right? Like in the stove with the damper open. But when you're in anabolic state, you are pushing that energy into growth channels. And this is like shutting the damper, right? You're limiting the flow of oxygen, um, and that is going to allow the fuel to accumulate. And if we think of an organism as a collection of cells, right, and all of the cells are communicating with other cells through the bloodstream, but they also are making their own internal choices. So if we think about something like obesity, if the adipose cells, if the fat cells decide that they want to go into growth mode, what's going to happen is they're going to start sequestering fuel from the rest of the body, and they're going to start building, right? And now the rest of the body is going to have to make choices based on the fact that the fat tissue is actually sequestering energy away, and so that might be a hunger signal, right? It's like, oh, where did the blood glucose is gone because the fat tissue used it to make fuel. Now I'm hungry again, right? And so we tend to think of things as humans. We tend to think of things as being the sort of the fault of the person, right? And so it's like, oh well, that person's fat because they're a glutton or because they're lazy. Mm-hmm. Whereas I believe that it is the system is more driven by the internal choices that the cells are making and the sort of state of the cells, and that is causing us perhaps to overeat because our hunger circuits are dysregulated, or simply that in a different state, even if we did overeat, that fuel would just burn away, and it's not really about caloric consumption at all. That is actually sort of more specifically what I believe. But so I go into the other thing I talk about is immune cells, because the immune response is a really interesting example of cells who, when you have an infection, your macrophages, when they see that infection, they immediately go into this different metabolic state, which is more glycolytic, right? And so when people think about cancer cells do have this thing called the Warburg effect, where instead of burning the carbohydrate, burning the glucose in their mitochondria, what the cancer cells do is they pull in the glucose and they do this process called glycolysis, and that lets them get a little bit of ATP from the fuel, and then they eject most of the carbon as lactate. So they're not it's a fermentation, really, is what's happening there. And so the cancer cells grow on that. But interestingly, at the beginning of immune response, the first thing that the macrophages do when they find like a bacterial infection is they become very glycolytic, because that makes them very growthy, right? That's anabolic. That's adding and building. And I point out in the beginning of the series as well that your fat tissue is also, if you're an obese person, your fat tissue is also in a glycolytic state, right? Your fat tissue is behaving like an activated immune cell. Your fat tissue is behaving like cancer cells. They've switched into this glycolytic state. And the question is, why did they do that, right? That's a state that favors growth, and it's an anabolic state, and it favors building. And so why are your fat cells preferring to build energy rather than burn fuel, right? Because I believe ultimately that is at the heart of how the thing works, right? The sort of decision, right? And the other thing that I talk about a lot is the fact that we look at obese people and we think, or diabetic people, and we think it's a pathology, right? Like something has gone wrong. I don't think about it like that. I think that mammals survived this thing called the Great Dying, or these were the things that were proto-mammals. There was this event even before the asteroid that killed the dinosaurs. There was another event before that was even more devastating than the asteroid impact, that killed almost everything on the planet. And the things that became the mammals survived that by essentially hibernating through it, right? They slowed down their metabolic rate, and they stored fat, and they somehow existed until conditions got better. And so that is, I believe that the metabolism has ways of determining, are we in a place where we want to, be burning fuel oxidatively? Are we going to be reproducing and growing, or are we going to, or is winter coming and it's our imperative, our biological imperative to fatten up and save energy for winter, right? And so I feel like, a lot of what I think about are the signals to the organism that represent either it's summer and we should be, we should be doing summer things, we should be reproducing, we should be dancing, or winter's coming and we should be in that fattening up state. I call this subclinical hibernation or subclinical torpor. I stole that phrase a little bit from, I started talking about torpor, and then Ashley Armstrong gave me the phrase subclinical torpor. But I like that now. I think we've adapted that.
And then there's a relationship with leptin and light, right? And that leptin signals satiety, right? And that has this relationship to light that's important here too.
Yeah, I believe that. And I do believe that red light is very supportive of metabolism. And when you think about it, right, when a lizard or a snake wants to get their metabolic rate up, what do? They go lie in the sun, right? And so I think that that red light is absolutely stimulating of the metabolism beyond just simply the fact that they get heat from the sun, right? I think the red light is unleashing those metabolic things. Mammals evolved from lizards who lay in the sun to increase their metabolism. So, and lizards do a thing called estivating, which is a lot like hibernation in mammals, right? But they tend to do it in the summer and through the dry season or through the hot season, but also in the winter. Snakes hibernate in the winter. And so there's this long history of needing different metabolic states to deal with different seasons on Earth, right? And so if you trick your body, send it the wrong signals, it thinks that winter's coming and it starts to fatten up.
Yeah, the lack of sunlight. Then there's the overabundance of blue light. Do you think that is just as big as PUFA with the obesity problem that America and the world has experienced? It's just, they kind of go along in the timeline, don't they? Or maybe
what?
I said they kind of go along in the timeline, right?
Yeah, they do. Well, it's all tied in. I mean, day length. I mean, it's very easy to show in the lab that if you take if you take a mouse and you put them into an 8-hour day, right? You just turn the lights on and off in the lab, but if you have the lights on for 8 hours and then 16 hours of dark, they'll get fatter than if you do 16 hours of light and 8 hours of dark, right? Because it's a sign that it's summer now. Mice are not the best example of that. If you do it with other more kind of animals that tend to hibernate, they do it even more dramatically. You can really affect how much they fatten up just by changing the amount of time that you leave the light on.
I know it's not the case, but wouldn't that mean that blue light would be kind of helping metabolism, or is it because?
Well, see, I mean, I would. So I wonder that too, and I don't know. I don't have the answer, right? I someday I want to do that experiment, but I question the same thing. Like, I wonder about maybe screen time in the fall as the days are getting shorter isn't such a bad thing.
Yeah. Huh. But then it's like artificial because it doesn't have the supporting other light,
right.
with it.
Yeah. Right. Doesn't need to be full spectrum light. I mean, these are all
maybe
interesting
you need to have maybe you need that full spectrum light, if you're going to do that. Have they done any studies on that you're aware of?
I don't know. I have not looked for studies on that specifically, but it would be interesting. It's an interesting thought experiment.
There's that guy, Jack Cruz, who's always talking about light. And I know he doesn't play nicely with the Ray Peat people and all this, but he's always talking about the importance of getting that sunrise light in your eyes.
Right.
Which is a lot of
light,
right?
Yeah. I mean, the sunlight has all the different lights.
Right. But that sunrise light is supposed to be very special for your metabolism and his thing. Yeah.
Right. I mean, I don't doubt it. I'm not sure.
Yeah. Yeah.
I do know that it's all tied in. One of the things. So one of the things I talk about a lot are nuclear receptors. So when right when life became multicellular, um, now you have all these cells and they're living in these communities and they have to communicate with each other, and a lot of that's done through nuclear receptors, right? So nuclear receptors are looking for specific compounds and then the cells react a certain way. So a great example of this is vitamin D, right? Vitamin D is a nuclear receptor. You make vitamin D from the sun. So vitamin D is kind of a classic summer signal, right? When the sun's made, vitamin D, it all happens. But other nuclear receptors are looking for things like the types of fats that you eat.
Yeah.
And one of those is something called PPAR alpha. And interestingly, I've kind of forgot the thread of where I was going with this. I was going to say that PPAR alpha is controlled by this thing called the aryl hydrocarbon receptor, which is this is where I was going, which is all linked in with fat metabolism, right? So fat metabolism runs through PPAR alpha and the aryl hydrocarbon receptor. But interestingly, the aryl hydrocarbon receptor controls your circadian rhythm. So when the AHR is very activated, it shuts down your circadian rhythm, and ordinarily what happens is you wake up and different enzymes are expressed during the day than are what expressed at night, right? And that's all controlled by these clock, this gene called clock, and another one called BMAL, blah blah blah. But it's a tightly regulated cycle, and if your fat metabolism gets overly activated, your circadian rhythm goes away. And so then you think, a lot of people with obesity also have insomnia. And then you think, that's probably a mechanism for how in the fall the bears are just like, I'm just going to sleep the whole fall, right? Because they've lost that circadian rhythm because of the types of fats that they have and how they're all signaling and how those signaling networks work.
That would seem if you're you said if you're over, what is it about your fat metabolism if you're overstimulating it?
Yes, if you're overstimulating it, these are the kinds of things. I mean, the aryl hydrocarbon receptor can be.
Would that mean that a ketogenic diet would affect your sleep eventually? Is that the idea there, or no? If you're running on metabolism, I know most Americans are running on fat primarily, anyways, right? Because of the standard American diet. Yeah.
Yes, I think that's true. Yeah, I mean it's tricky, right? It depends on the types of fats, and it depends on the a lot of the things that affect like PPAR alpha are oxidized fats, and so like a really bad one is fryer oil because those are oxidized, and also trans fats, right? Like I grew up in my house we had margarine, we didn't have butter, and so I was eating these trans fats that were activating that part of my metabolism all the time, right? Every day I had this overactivated PPAR alpha because the trans fats are specifically activating of that nuclear receptor. Same thing with fryer oil, especially made from vegetable oil, right? Those make compounds that really overactivate that side of your metabolism, and so you can burn fat and eat fat and use that side of your metabolism without dysregulating it, right? It's the oxidized things and it's the weird stuff that kind of really overacts it. And there's a lot of things in the environment as well. So I just went to a conference on finding PFAS with using gas chromatography or gas and or liquid chromatography. And so PFAS is a thing. It looks a lot like fat. This is what Teflon is, like nonstick pots, right? They I think they stopped making Teflon a decade ago, but I grew up with Teflon pans, and so Teflon is slippery like fat. It's like grease, but you can stick it to the pan, and so Teflon is chemically it's very similar to a fat, except that the hydrogen, fat is a hydrocarbon, right? So it's a bunch of carbons with hydrogens attached to it. Teflon is a bunch of carbons with fluorine attached to it. And so the Teflon looks like a fat to an organism, but it's a very different thing, and it activates PPAR alpha. It helps to dysregulate um, that part of your that part of your metabolism. It helps to dysregulate fat metabolism. And there's a lot of other plastics, right? The chemicals from plastics are affecting these nuclear receptors in your endocrine system. Pesticides, herbicides, all of these things are endocrine disruptors. When people say endocrine disruptors, that means it's affecting your nuclear receptors. That is your endocrine system and how it works. And so you have this combination in the U.S. in the last half of the last century of sort of rising consumption of these unsaturated fats, vegetable oils, and high in omega-6, but also high in monounsaturated fats than we were before. And I think those both play a role. And you have that in an environment where we're increasingly contaminating ourselves with these endocrine disruptors that are activating that whole endocrine system. And I believe it's the combination of those two things together that have really thrown everyone off track. And so now we're
way more than the lack of sunlight and the increase in blue light, in your opinion there.
Well, I think it all matters, right? Like, I live in New York State, right? So I live in an area where the daylight goes up and down. So I'm already, just by living in New York State, I'm already putting myself into a situation where my body in the fall thinks winter's coming, right? Because it sees the daylight getting shorter and the sunlight's going away. So that being the case, you have to be, you can't also have all the endocrine disruptors and the vegetable oils, right? So it's like, right. How much do we want to, you might be able to overcome one or two things, but can you overcome 8,
Yeah.
And so that PFAS, the thing that looks like fat is in America. No one has yet found a sample of American blood that does not have detectable levels of PFAS. Not a single American has undetectable levels of PFAS. Wow. Because it kind of bioaccumulates. It's in everybody's water. It's in, where they would use it is in linings of like microwave popcorn bags. Yeah. They would line it with this substance to keep everything.
They still do, or this is what they used to?
I think some of them still might. Like, I thought that these things had all been
get Bobby on that. Get Bobby
outlawed, or they moved on, but I kind of think that some things are still using them. Like
Bobby's choosing violence lately. He's been firing his CDC panel, so you never know. He might go after that PFAS if we get him hyped on.
Well, he should go after the PFAS. Yeah.
How do you get out of the system?
It was 3M. It was 3M that started making it. And you know what else it was in is like that, like Scotch Guard, the lining that you spray on your couch so that if something spills on it, it doesn't stick. That's all made with PFAS.
Wow.
Raincoats are coated in PFAS.
Okay. And then that Windex, the Rain X that you spray on your windshield.
Probably.
Yeah. Dear God. Now, is there any way to get that stuff out of your system, or they're going to try to come up with the mRNA vaccine on that one? Don't give them ideas.
I don't know if you can vaccinate against that. No,
they'll try. They'll try. I didn't know you could vaccinate against a lot of stuff.
Levels in the atmosphere are coming down because they realized what was happening, and we stopped using it in as many places, and it is slowly getting better. But we're already poisoned, so
there's no molecule that you can use in there that'll latch onto that PFAS in your blood and get it out of there or neutralize it.
Not that I know of, but it's another potential area of future research, I guess.
Yeah, man. If only there was a group that was really dead set on finding out the answers to these things, maybe we'd have a chance one day, right?
I think there should be a group like that someday.
Yeah. I think so too. Because there's so many things hitting you all at once where you're just bombarded by, this thing and that thing and this thing and that thing. Everybody just wants to get back to a normal life. You know,
Absolutely, right? It's like,
nobody
why does
wants
it
to
have,
be neurotic about everything they touch. For God's sake,
right? And
it's
how
gonna be
it
so
shouldn't
toxic.
it shouldn't be this hard just to
Yeah,
be a healthy human being, you
yeah,
know?
exactly.
Um,
Like what you
and
probably cook with what, like an iron skillet or something, because you're like a foodie, so
yeah,
you're smart about
or or stainless
stainless.
steel.
Yeah,
They they do have new nonstick coatings that are made of ceramic
yeah,
materials that are probably all right, and they I don't quite understand how the ceramic sticks to the pan, but the new nonstick materials are, I think, much better than the PFAS ones. Um, but yeah, my mother has those, and they're actually pretty cool. I was like, these are neat, you know.
yeah, yeah. Well, I really appreciate you coming on, Brad, and I know that we didn't cover everything, but you did mention the Cambrian explosion in one of your latest posts called "How We Handle Hypoxia." Did you get on that topic?
Of the Cambrian explosion, yeah.
Yeah,
So there's an interest. So when you look in the fossil record, you go through the sediments. You find in the sediments that are younger than 520 million years old. You find all these fossils. First, you start finding trilobites and then all the others. But before that timeline, before about 520 million years ago, fossils are really rare. There are fossils. Um, the oldest thing that is clearly a fossil is a sponge from around 600 million years ago. Um, there's potential evidence of sponge fossils from more like 900 million years ago. Um, but but then suddenly, boom! It's like there's all these new life forms and all these new fossils, and so that is a key moment in all of this when that happens, and our um, the first thing appears at this moment that is again, I talk a lot about clades. So in evolutionary biology, a clade is the thing that your lineage evolved from. And so like humans would be in the clade of primates, right? But we would also be in the clade of reptiles, because it seems that we evolved from lizards. And you can go back all the way, and so but we wouldn't be in the clade of, right. So I'd say we were in the clade of reptiles, but we're not in the clade of snakes, because we didn't evolve specifically from snakes. So they're parallel, or they're off to the side of the core, right? Um, and so so that's how we think about it. But anyway, the reason I'm long-winded way of saying it, but the first thing that looks like our clade shows up right at the Cambrian explosion, and that is a thing called a lancet, which is kind of looks like a little fish. It's like almost halfway between a fish and a worm, and these things are still around. They're easy to catch. You can catch them at the beach, and they're just little. They're little, but they have what's called a notochord, which is the thing that we believe eventually became the spine. And so, the lancets are kind of the oldest thing that is clearly sort of like our clade, if you want to think about it that way. So that's an important moment. And one of the things I ask, if the goal is to sort of reverse engineer our metabolism, the reason I'm so interested in this evolutionary stuff is the question is, what components of the metabolism were in place first, right? Because the thing that's there first, everything else kind of evolves around that over
yeah,
time. And so I look and I'm looking and I'm trying to find the fundamental drivers of how do the cells make this decision about um, are we going to be glycolytic and growthy, or are we going to be adult and differentiated and not grow anymore, right? And so we're started to look at an example of how the immune system makes that switch into that very glycolytic anabolic mode, and make the evolutionary point that these these lancets, this amphioxus has, right? Because the thing is, you can just catch them now and you can look at them and say, well, do they have macrophages? And you're like, they do. They have something that's very much like a macrophage. And do they have the same genes that we see in our macrophages that determine this switch to the glycolytic growthy state? And you say, yep, there they all are.
Mm-hmm.
So these, so 520 million years ago, the system had evolved to switch back and forth from differentiated to glycolytic and growthy and STEMI and cancery and whatever other words you want to use to call that, in this 520 million year old lancet called Pichia, I think is what they call that one. And so then that is at the root of the story, right? That's at the core of the story, and then we grow from there over time as new things are sort of layered on over the others. I call that that part of my theory, I call the onion of biology, because what happens is, as animals become more evolved, you don't go in and change the underlying layers. You just add a new layer of control on the top of it, right? So like, glycolysis is a good example, right? Cells take in glucose and it goes through the series of reactions, and humans do it the exact same way that bacteria do it, right? It's the same system of enzymes. It's the same products come out of it. And so that is something that has been the first thing that we can call a cell in those thermal vents. Could do glycolysis, and it could do the pentose phosphate pathway. Those are the two alternating pathways. And glycolysis is they play opposing roles, but so that's like the core. That's the core layer of the onion. And then when you get up to amphioxus, now we've layered on NFKB and NRF2 and PPAR alpha and all of these new higher level control kind of things that are involved in immunity, but mostly they're involved in this switch to the glycolytic growthy state. And so we wrap that layer on, and then as we get closer to modern times, we'll be wrapping in new innovations and seeing how they all work. And then we're going to look back at this weekend. We're going to revisit our copepod friends who have swum deep down in the ocean to fatten up and see why they're doing that. And that's the big bombshell that's coming that has to do with PUFA, which I think is going to be, it's very exciting.
Well, very good. Did you since we last talked, which about a year ago, I guess, have you learned things that have surprised you or shocked you or changed your mind in different radical ways? Yeah.
Yeah. I mean, all the time, right? Like, so just this from this article that just came out about PPAR alpha, the involvement of PPAR alpha in immune cells when they undergo this, they call it the respiratory burst, mm-hmm. right? And this is when they suddenly that's when they become glycolytic and they ramp up their metabolism and they start cranking out reactive oxygen species. That's what your immune cells do. They have mounted on the outside of the thing through the membrane is this thing called NOx, which stands for NADPH oxidase. Mm-hmm. And it just unleashes a stream of superoxide, and that superoxide kills bacteria. And so we're literally oxidizing the bacteria to death. And one of the things that is fascinating is that if you block PPAR alpha, which is involved in polyunsaturated fat metabolism, and it's not fat is not capable of burning in the mitochondria and that glycolytic state, and it's not contributing to the NADPH pool. So why is the PPAR alpha necessary to continue this glycolytic response that generates this stream of reactive oxygen species? Right. And I only realized this maybe, I don't know, a couple of months ago, because I think a lot about PPAR alpha and what is it actually doing, because it's it's involved in all of these different processes that seem disconnected. And so that surprised me that PPAR alpha was actually necessary to sustain that burst of ROS. But then the more I thought about it, I said, okay, this actually is very sensible and it makes sense now. So that's what I'm going to write about this weekend. And it's how it's essentially how cells use polyunsaturated fats to maintain that glycolytic growthy state. So that's very exciting, and it's pretty new. Like, it's pretty new to me as well, and I'm excited to talk about it.
Yeah, I'm excited to see how all these different layers, my chief science advisor for our program, Dr. Yu, says that everything is magnetic. All particles are fundamentally little dipolar, positive, negative little magnets. And I've seen so much information over the year that I think he's right. And so I've been following that journey as it aligns with more and more accumulating evidence. And then along the way, you meet other folks who have an interest, like Dr. Pete, about the PUFA. Then I meet, you're doing stuff too. I think I met you first before Dr. Pete, but yeah, I did. And so all of these different voices kind of coalescing around these different layers of life. And you have things like magnetism, you have light, right? And you have these gases, oxygen and carbon dioxide and water and what and everybody's got an emphasis on their particular thing. And I just want to see it all harmoniously play nice together so that the truth can come together. You got some people that are all about this thing or that thing to the exclusion of all these other factors, and everybody, not everybody can be an expert about every topic, but I want to see it all coalesce together so we can give something to the next generations, which is far superior to whatever we've learned. And that's how civilization is going to continue, no matter what happens with the nuclear wars and all this other stuff people are worried about. You've got to have something that's superior of information passed down to the next generation and the next generation in order to advance the species.
Yeah, I couldn't agree with you more. And we're all here just fighting a good fight, trying to.
I want to see
figure out all these mysteries.
I want to see how you bring in the naked mole rat into the conversation with the rabbit and the woodchuck.
Yeah, well, I think that's a good suggestion.
See all of them lay together and see what's going on, the differences.
I'll do some digging on them.
Yeah,
literally. See, that was unintentionally clever.
Very good. Well, we figured that you'd have some real fun things for us catching up. So I hope we'll do these more often as you're on season right now.
Yeah,
Brad Marshall is on season right now.
That's right. Let's keep doing it. We should do another one once these new articles come out, and we can talk about the new revelations.
Yeah, fireinabottle.net is his website. It's fireinabottle.net. And anything else you'd like to leave us with?
That's a big thing. I'm going to be launching a new podcast with Ashley Armstrong this summer/fall as well. So this is maybe the public unveiling of that fact.
Well, very cool. So we'll look forward to that.
She said that I should not keep it a secret, and I should come on here and promote it. So that's what we're doing.
Well, that'll be a fun podcast to look out for. So we'll be looking forward to that one.
Yeah.
All right. Take care.
All right. Take care, David.
I took the